Okay, and we reset this. Reset, start. Okay, and then we take a drink of tea. Okay, so this is Supowit's algorithm. Why is it correct? Well, before we take any steps, our empty sub-solution can be extended to an optimal solution. I feel kind of silly doing this, but I don't want you to forget. So look, if you get to the midterms or you get to a final and you're like, I have no idea how to do this question, but you think it's a greedy algorithm, then first, as I told you, sort by whatever you can think of, and at least write down, and this algorithm is correct because before we take any steps, our empty sub-solution, because then and then you get to the thing of like, and then we assume that after I steps we haven't made a mistake, and you're like, yeah, I don't at all see how the exchange argument works, then you can at least say, and then we do some exchange, and so after I plus one step. So I'm going to warn the marker to watch for this, but you can at least try. A Supowit without the Z. Already carved the whole sentence at the end. Okay, sorry about that. That sounds painful. Okay, why does it? So before we take any steps, our empty subsolution can be extended to an optimal solution. So let's say that we've done. I'm just going to erase these up to say here. No, I'm not. I'm going to put the 6. Yeah, those two are still going to be the same. And we're going to do this with the 6. Okay. Oh, this is actually easier with the finger. I hope this stuff is not toxic. Okay. So let's say we had 7, we don't have 9, 2, 4, we don't have 6 and 8 yet. Oh, I can do that with the eraser at least. At least minimizing my exposure to 3 we've got, but not 5 and 7. 1 and 2 we've got, but we haven't got 4. And 3 we haven't got. Okay, so let's suppose that up to before we take any steps, our empty subsolution can be extended to an optimal solution. After we've taken any step, assume that after we've taken any steps, our subsolution can be extended to an optimal solution S. Okay, so there is a way to fill in the rest of this stuff such that we get an optimal solution with a minimum number of subsequences, of increasing subsequences. We show that after I plus, so you do this exchange argument, after I plus 1 steps, you can, our subsolution can be extended to an optimal solution as prime. So let's suppose that we're looking at the 6. So up to here we haven't made any mistakes. But so we're going to put the 6 after the 4, right? Oh, right, so I should just write this down. I don't think, this is not in the book, and nobody teaches it usually, I think. It just came up in something I was doing, and I can use it because in dynamic programming we're going to see finding the longest increasing subsequence. That is a classic problem. And so I think last year I managed to fool people by putting this on the assignment, and they all had it driven into their heads that you do problems about longest increasing subsequences with greedy algorithms. And then I turned around and taught them the dynamic programming, and people got confused and didn't know what to do on the exam. So, somebody's waiting. So it's nice because as I told you at the beginning of the course, don't just pattern match. Don't just think, ooh, this is an increasing subsequence problem. We're going to do this with greedy. You actually, algorithms is not that easy. If it were, I probably wouldn't have a job. Maybe. I mean, I'm a researcher, but if it were that easy, I probably wouldn't have a job as a researcher either. Okay, so let's suppose we put the 6 here, okay? But let's suppose S, this optimal solution that extends our solution, let's suppose S was blue, right? S puts the 6 here, okay? And we think, oh, okay, so now S doesn't extend, we put the S here, so I'm going to write that in green. But we put it here, S puts it here, and we think, oh, so now S doesn't extend our solution anymore. Well, what can we do? So let's think about this. Then you have to, the rest of S puts some stuff here. And maybe S starts some other chains here. Okay. And S is going to put, so we put the 6 here, but S is going to put some other stuff here. Okay? And then it's going to put some stuff after the 6, and maybe it's going to put some stuff after the 7. Okay? So let's call this A, and, well, actually, we're not going to move that. So let's ignore that. So what are we going to do? Let's call this A, and let's call this part B. Okay? So, actually, let's call all of this B. We're going to leave the rest of S's solution alone, but we're going to switch A and B. Okay? So that is going to put the 6 after the 4, which is where we want it, where we put it. And why can we do that? Well, we put the 6 after the 4, and the rest of everything we're going to leave alone. Okay? And so it's S's solution, and so it was optimal. So why can we do this switch? Well, 6 goes before. 6 is larger than 4. Otherwise, we couldn't have put the 6 here. So whatever element we're considering was 6. It has to be. We're putting it after the largest thing that we can put it after. So S had to put it either as its own chain, or it had to put it after something smaller. So we can move the 6 here. So we can swap B here. Why can we swap A to after the 3? Well, we put the 6 after the largest thing we could put it after, which means that whatever S put it after, either it's its own chain, in which case A can always become its own chain, or if it put it after something else, it had to be smaller. So 3 is smaller than 4. So if this is, for example, 8 or something, it has to be larger than 4, and 4 is larger than 3. So this is larger than 3, so we can actually put we can put A after here. So we can swap A and B. And that is not going to increase the number of chains. Because we're just swapping something. If B is its own chain, we're swapping B to A, and A is becoming its own chain. We're not changing the number of chains, so we're going to get a solution which has the same number of chains as S, so it's also optimal, and it's putting the 6 where we want it. Okay? So after I plus 1 steps, our subsolution can be extended to an optimal solution S. Therefore, by induction, we obtain an optimal solution. Okay? Questions? Everybody good? Anybody still there? Nobody's in the waiting room? Okay. Now, I don't know, people like last year or the year before, they found this really tricky, probably because I put it on an assignment without teaching it to them. Okay, so now, vertex cover on trees and a little bit on graphs. So I don't know if we have time for the bit on graphs. Okay, vertex cover. To remember what a vertex cover is, remember this phrase, it's a vertex cover of the edges. Okay, so if you have a graph, you have some graph, a vertex cover is a subset of, so vertex cover, I should write this down. A vertex cover of a graph G is, okay, G equals, is a pair, the vertex set and the edge set is a subset of V, subset, let's say S, subset S of V, such that for every edge in the edge set, one of the endpoints of E is in S. Okay? At least one of the endpoints. So, A, B, C, D, E, F, G. Does somebody want to pick a vertex for this graph? Anybody there? A. Okay. People like starting with A. Okay. A. Somebody else want to choose E. Now notice A covers this edge and this edge. E covers this edge, this edge, this edge, and this edge. So I'm just going to slash. So somebody else choose another one. C. C covers that and that, and another one. D. Well, actually, okay, so I'm gonna, D doesn't cover anything now, but probably you wrote D at the same time that somebody wrote C. So starting now, write the next vertex you want to take. F. So actually it doesn't matter because both of these will cover this and then we're done. Okay, so F. Okay, so this graph has vertex cover of size 4. Does it have a vertex cover of size 3? I can't see one offhand. No, I don't think so. No, I don't think so. So you need one of these two. You need one of these two. You need one of these two at least. Yeah, if you take this one, yeah, okay. So I don't think it has a vertex cover of size 3. We don't need F. We do need F because we need either F or G to cover the edge FG. One of the endpoints at every edge. So if you look at the red vertices, all of the edges have some endpoint. I mean, this one has both endpoints are in the vertex cover. But all of the others, they have, and this one has both endpoints, but this is at least. So it's one, or I can have both. Okay. So, vertex cover is one of these nasty hard problems that we don't know how to do. Okay? Super easy to explain, and people have been trying to solve this. We can do it. I mean, obviously we can do it. It just, we don't know how to do it in polynomial time. Okay? Nobody has ever found a polynomial time algorithm for finding the smallest vertex cover. So if somebody gives you a graph and says, is there a vertex cover of size k? We don't know how to do that. In time polynomial and the size of the graph. Okay? So that's kind of frustrating, but there are, so this is going to, so I want, the next bit I'm going to tell you, can you explain that again? If somebody gives you a graph and says, and a number k, so they give you a graph on 10,000 vertices, and they say, is there a vertex cover of size 2,000? So you're allowed to choose up to 2,000 vertices out of these 10,000 vertices and try to cover every edge. We don't know how to do that. So given a graph and given a number, we don't know if we don't have a polynomial time algorithm that lets us tell if there is a vertex cover of at most of that size. So a vertex cover is you can always add extra things to the vertex cover. So you can always say it's size k, exactly k, because you can always just add stuff if you want. We don't know how to do that. Okay. So what we can do is some instances. For example, trees. We can do this on trees. We can find a minimal vertex cover, sorry, not minimal, minimum vertex cover on a tree, a finite tree, let's say. If the tree is infinite, then some stuff is going to be a bit weird, but let's say a finite tree. Okay. So I'm not sure I'm going to get to, you can do, there is an approximation, there are better approximation algorithms, but there is an easy approximation algorithm for graphs that I'm not going to show you today. But we can show, we don't know how to get a smallest vertex cover on a graph, but we do know how to get a vertex cover that's at most twice the size of the smallest vertex cover. And I will either cover it today or I will cover it when we get to NP-complete NP-complete problems. Okay, so let's build a tree. Okay, this is a tree. Okay, so I mean at least one of them. Yeah. Yes, it has to have at least one of the endpoints. Okay, so you would think when I say there is a greedy algorithm for doing this, you would think what's the obvious way to process the vertices? Right? What's the greedy way to do this? You're trying to cover the edges with the vertices. I think there's an obvious thing to do. Well, how do you sort the vertices? Right? You're going to have to consider the vertices in some order, and then you're either going to take them and put them in your vertex cover, or you're going to throw them away. That is the obvious thing you would do. That is not how the algorithm works. Okay? Which makes me think I should have saved this up for the exam or something. But no, I'm actually going to tell you this. Yes, like, that is the thing that you would think you would do, but you don't. Instead, you actually start with a leaf, which is the thing with the smallest degree. Okay, it's only got degree 1. You do not take the leaf. You take the other end of the edge. Okay, so we're going to take this leaf, and then we're going to take this vertex. Okay, and now we're going to ignore. We're going to draw that. Okay, we're going to draw this in green, in blue, and this is good because my blue is kind of faded. So, and actually we're going to draw this edge in blue too, because we've covered this edge. So now, we don't have to cover this edge, we don't have to cover this edge, so now we're just considering the stuff that's left in black. Okay, so now we find another leaf. We find this leaf. We do not take the leaf, we take the other end. We find a leaf. Let's say we take this leaf. We do not take the leaf, we take the other end. We find a leaf. Let's say we go up here. We do not take the leaf, we take the other end. And we've covered these three edges. Blah, blah, blah. Okay, we do not take the leaf, we take the other end. Okay. And so on and so on. So now we find the leaf. Okay, which leaf do we want? Let's say we take this leaf. This wasn't a leaf before, but it is now. So we take this leaf, we do not take this leaf, we take the other end, we take this, and that, we get all of the vertices. Ha ha. We get all of it, we cover all of the edges. We're done. Okay, so our vertex cover is, that we end up with is 1, 2, 3, 4, 5, 6. Okay? And I claim that that's the smallest possible the smallest vertex cover possible for this tree. Okay? Why? What's the magic words? It's not please in this case. Why do we know that this algorithm is going to produce a smallest vertex cover? And I'm concerned that this is, we have 1 minute and 42 seconds before. I'm just going to make sure that the small camera is recording because it's vital today, because we're probably not going to get a decent recording on a Zoom. Is it log of vertices? No. No, because for example, if the tree is a path, you have to do every other vertex. So that's actually half. Yes! Before we do anything, before we take any steps, our empty subsolution can be extended to an optimal solution. So before we have processed, before we have considered any vertices. Now this is an interesting case of a greedy algorithm, because you start, you sort the vertices by degree and you consider the leaves first. But notice that after you take stuff off, after you pull the leaves off, something that was not a leaf before can become a leaf. I feel like we're in a cult. I have never thought of it that way. Okay, so that means that you have to resort, right? So once I've pulled this leaf off and this leaf off, once I pulled. Where was it? Yeah, once you pull this off and this off, this becomes a leaf. Okay, so you have to resort. So let's suppose that after some number of steps, which we're going to do, So before we take any steps, okay.